Very good afternoon, everyone. I'm Dr. Tay Ziong from the Singapore Institute of Technology, and I'll be the moderator for the technical session today. On behalf of the Singapore Society of Floating Solutions, I want to welcome everyone to this technical webinar organized by the Society. We are honored to have Dr. Stephen Hoopner, a Senior Research Fellow from the Asia Research Institute, NUS, give us a title, Earth Amphibious Transformation, Tanguy Kenzo, Buckminster Fuller, and Marine Urbanization in Global Environmental Thought from 1950s to present.
Okay, thank you very much, Jo Young, and also everybody who was involved in inviting me, and welcome everybody. This presentation is largely based on two articles that I recently published in Modern Asian Studies and in Asia Global Online, and I added the links to them to one of the last slides of the presentation, since I think either the slides or the video will be shared among interested audience members. So Earth's surface is experiencing what I call an amphibious transformation. And before I talk more about the amphibious transformation itself, I want to emphasize its importance by briefly addressing one of its outcomes. On 3rd April 2019, United Nations Deputy Secretary General Amina Mohamed, who previously had served as Nigeria's Minister of the Environment, addressed several of the 21st century's environmental challenges at a high-level UN roundtable on sustainable floating cities. I quote her, "Floating cities are a means of ensuring climate resilience, as buildings can rise along with the sea. And when entire floating communities are designed from scratch, they can be designed to be neutral from the onset." End of quotation. In her speech, Mohamed summed up several ideas on how to adapt to these planetary challenges. In terms of climate resilience, floating structures not only rise with the sea level, but are also hardly affected by floods. Moreover, designing a floating city or settlement from scratch means that there's potential to create an environmentally sustainable structure using renewable energy generation and electric-powered public transportation systems. Offshore, solar energy generation is on average 10% higher than onshore. In the context of climate change, environmental degradation, and rising sea levels, which have affected many Asian and other coastal cities, such ideas and practices of floating structures have been gaining global significance. After all, organizations such as the Intergovernmental Panel on Climate Change or the Global Center on Adaptation have emphasized that climate change mitigation alone is no longer sufficient, resulting in a need for both mitigation and adaptation. My presentation's main question is how and why cybernetics-based designs for Tokyo Bay from the 1960s have shaped political and environmental ideas for large-scale marine urbanization, which is turning into an important part of Earth's amphibious transformation. My focus is on Japanese star architect Kenzo Tange and his university laboratories, or Tange Labs, planned for Tokyo 1960, which was released in very early 1961, and on world-renowned US designer R. Buckminster Fuller's and his team's floating design called Tetrahedronal City, first proposed in 1966. What I call Earth's amphibious transformation continues to move urbanization and industrialization onto the surface of the sea. After all, through the amphibious transformation beginning in the early 20th century, both terrestrial places and marine surfaces have turned into human habitats. I call this transformation amphibious since it did not result in a change of the physical properties of marine regions, as would have happened in the case of terrestrialization through land reclamation, an example of which you can see on this slide. In contrast to largely two-dimensional solid ground on land, such marine spaces remained volumetric, meaning three-dimensional, liquid, and unstable. I call it a transformation since spatial practices strongly changed when communication system expansion offshore turned isolated marine surfaces into places associated with human settlement. Where once only individual ships could signal each other upon meeting, radio and later satellite technology connected marine surfaces to more advanced terrestrial communication systems, eliminating the spatial divide of isolation between network-connected offshore and onshore spaces. For example, thousands of floating or fixed oil and gas platforms have enabled humans to live permanently offshore and to be connected to global communication networks. Other floating or fixed offshore structures whose construction was enabled by communication network expansion, and new communication technologies include liquefied natural gas or LNG terminals, or helipads, space rocket launch platforms. You might have read about SpaceX recently, oil storages, mariculture or marine organism farming facilities. One of them can be seen here. Military installations, wind turbines, nuclear power plants, here the Russian one, solar panels, here's one in a lake in Indonesia, and here one offshore in the North Sea of Norway. Hotels, mass-produced high-tech floating homes. Here's a student dorm in Copenhagen, the floating pavilion in Rotterdam, the float at Marina Bay here in Singapore. And these offshore structures are accompanied by cruise ships, aircraft carriers, factory ships for freezing and processing fish, or earlier on also whales, and so on, all inhabiting marine and other aquatic surfaces and constituting unconventional forms of settlement. In terms of its temporal dimension, the amphibious transformation evolved roughly parallel to what I call a terrestrial mindset. Before the 20th century became globally dominated by this terrestrial mindset, humans adapting to amphibious habitats was not uncommon. A growing historical and anthropological literature on Asian river deltas showed how the regular presence of water and related environmental conditions shaped the awareness of people and their settlement practices. For example, in Asian river deltas, perennial floods resulted in amphibious settlement practices like stilted houses or raft houses, the latter floating when the water arrived. In terms of adapted agriculture, in some regions, floating rice with fast-growing stems survived water level rises of more than 3 meters. Other studies addressed, for example, Ebunu or boat people from Japan's Seto Inland Sea, and other boat people who for centuries adapted themselves to life on boats. Urban studies showed how even during the 20th century, such boat dwellers created unplanned forms of urbanization in Tokyo and other cities. What many of these studies emphasized is that terrestrial authorities discriminated against their non-terrestrial way of life, tried to remove them, and associated floating or amphibious settlement practices with low-tech or primitive living conditions. And there is some truth to that. In the following, I employ a perspective that goes beyond the far-spread terrestrial mindset. I analyze the amphibious transformation of Earth's surface from the perspective of the cybernetics boom in urban design, which radically changed design ideas and during the 1960s turned Tokyo Bay into the birthplace of high-tech marine urbanization ideas, which I would like to differentiate from the just mentioned earlier low-tech structures. Fuller and Tange were leading transnational figures in the urban design-related branch of the global cybernetics boom. The cybernetics boom focused on blurring borders between biological and artificial systems of communication and control. It was caused and driven by the communication technology revolution that has taken place since the 1940s. Cybernetics is regularly described as the dawn of the information age and evolved from MIT mathematician Norbert Wiener's eponymous book, published in 1948, even though its ecological references were increasingly overshadowed by the non-biological language of IT or information technology. Initially focusing on modeling how the very first electronic digital computers or electronic brains operated, cyberneticists considered artificial communication systems to replicate biological ones. Operating through feedback loops, such biological communication systems, like the neural networks of brains, enabled and coordinated an organism's interaction with its environment. Retrieving and processing of information, reactions based on achieving a certain task or goal, followed by a renewed environmental interaction. This new way of modeling rapidly spread across academic disciplines, including architecture, where it resulted in novel urban designs centered on communication systems. I want to argue that Tange, Lab, and Fuller, applying their cybernetic models, designed artificial communication systems that, by replicating biological processes, serve to expand urban design practices to marine surfaces by eliminating the spatial divide of isolation between them and terrestrial places. Moreover, the communication technology revolution allowed Tange Lab and Fuller to design marine urbanization structures that utilized such communication systems, which controlled and operated communication, but also transportation and energy networks. For example, on land and at sea, human nervous systems, meaning biological communication systems, were extended or connected to each other through artificial networks created by radio, computers, telephones, telex, TV, CCTV, as well as transportation devices supported or guided by radio, and so on. As mentioned, we are talking about the 1960s. Consequently, I also want to argue that Tange's and Fuller's biomimetic model of communication control aimed at using communication technology to replicate in floating or elevated structures the biological processes of growth, mobility, adaptation, and ecological autonomy, meaning these structures' self-sufficiency, which then became the central environmental political approach for moving urbanization offshore and reducing its ecological footprint. The cybernetic designs served to limit Tokyo's horizontal urban sprawl, partially removed urbanization from immobile terrestrial space, and maximized the lifespan of modular elements, which all correlated with a reduced attendant pressure on ecosystems. So why Tokyo Bay? But during the late 1950s and 1960s, Tokyo Bay became the target of discussions that focused on Japan's escalating urban sprawl, population growth, and the related transportation network congestion. One answer was to stop or even reverse sprawl by redesigning the city and by using the bay as an urbanized place of high population density. Tange, who was already a well-known architect, would become one of the major voices in the Tokyo Bay debate. After graduating from Tokyo Imperial University in 1936 and some time spent working in colonial Manchuria and other places, he returned to the university, first as a postgraduate student and from 1948 as faculty member, opening Tange Lab. During the post-war period, he gained international fame as the designer of the Hiroshima Peace Memorial Museum in 1952, followed in 1961 by the unrealized Plan for Tokyo. As the most well-known Japanese architect of the 20th century, Tange designed more than 100 buildings, districts, and cities across the globe. Tange Lab's plan, and before it, the ideas of some of Tange's mentees or students, were inspired by the problems related to terrestrialization through land reclamation. The lack of stability of buildings that were erected on a huge reclaimed space was a concern, since it necessitated the use of piers standing on the solid rock of the base floor, which would mean both land reclamation and pier construction below the buildings. So Tange Lab skipped the idea of land reclamation in favor of only using piers. This is important since both Tange Lab's and Fuller's designs serve to circumvent such large-scale land reclamation, its financial costs, and its permanent environmental footprint. Doing so, however, became the preferred solution for Japanese civil servants. To be sure, land reclamation had a long history in Tokyo Bay. However, the aforementioned amphibious or floating adaptation approaches of Ebouno and others also had a long and partially urban history in Japan, Asia, and globally. Japanese civil servants opting for land reclamation instead of elevation or floating structures as their preferred solution, therefore represented the terrestrial mindset that had gotten dominant in Japan and whose historical origins I now want to briefly address. One of the main hindrances of marine urbanization was, I argue, that the 20th century experienced the worldwide land reclamation, hydroelectric dam construction, and coastal defense upgrading boom, globally causing or intensifying the terrestrial mindset that turned water into an object of fear and danger, since it can damage coastal structures, including terrestrial Japanese nuclear power plants, as we know. In contrast, amphibious or floating architecture did not suppress or bar water flows. Instead of trying to control nature, the aim was to reduce vulnerability and prevent significant damage by adapting to regular floods and more sudden changes in water level. Of course, the hydroelectric dam construction boom since the late 19th century created water reservoirs. But my point is that a far greater area experienced a land reclamation process through the control and removal of waters that had perennially flooded amphibious environments. This terrestrialization process changed amphibious spaces like river floodplains or coastlines into places where terrestrial settlement and industrialization strategies could be applied. The related terrestrial mindset that shaped regional development projects therefore devalued amphibious or floating adaptation approaches, such as wooden stilt or raft houses, as pre-modern, low-tech, and primitive. In Japan, since the late 19th century, hydroelectric dam experts began to transform the landscape, and since the early 20th century, also its colonial empire in Korea and later Manchuria, where terrestrialization and the related promise of regional industrial development also became a tool to legitimize colonial rule, in addition to a number of other reasons, such as later on the industrialization for military purposes and so on. After World War II, leading Japanese dam engineers continued their careers by utilizing the demands for reparations. These reparations were paid in part through construction projects, such as Burma's first dam, built between 1954 and 1960. In the late 1960s, such Japanese experts also, for example, convinced the Indonesian government to construct the Asahan River Dam in northern Sumatra. Similarly, China, India, South Afghanistan, the Mekong and Chao Phraya river deltas, and other parts of Asia experienced a hydroelectric dam building boom for irrigation and energy generation purposes. While in the 19th century, hardly any such dams existed in the world, now there are almost 90,000, the vast majority of them located in Asia, or rather in China. I see such projects as strong contributions to and expressions of the terrestrial mindset in regional development. And on this slide, you can see the relatively well-known Anthropocene charts, which were created by the Anthropocene Working Group around 2015. They include one, bottom left, on the rising number of large dams, emphasizing their planetary scale environmental impacts. By taking a perspective that goes beyond the terrestrial mindset, I will interpret Tange Lab's plan and Fuller's tetrahedronal city as countermodels to hydroelectric dams and land reclamation. They were therefore also regional development projects, but they rejected the terrestrial mindset in favor of elevation or floating design. I cannot introduce the plan for Tokyo in detail. However, you can find these details in my article in Modern Asian Studies. I will limit myself to explaining how the plan promoted cybernetic ideas of modularization that became an important characteristic of later marine urbanization ideas and served to distinguish them from projects shaped by a terrestrial mindset. Tange's string of ideas began with the analogy of leaf-bearing trees and the authority of trial and error proven evolution of biological communication systems. A leaf-bearing tree's internal biological communication system allows it to sustain itself by operating the seasonal growing and discarding of its leaves. So the automated biological communication system determines when to grow and when to discard leaves and implements the process. In September 1959, Tange attended a major architectural conference. There, he also gave a presentation in the name of Kiyonori Kikutake, one of his mentees. Tange explained that in Kikutake's cybernetic understanding of new architectural forms, a long-lived or permanent structural element represented a tree's trunk, while short-lived or modular elements built on it, such as individual dwellings, represented leaves that can be grown and discarded, or attached and removed, if you prefer that, whenever necessary. This analogy goes back to Kikutake's tower-shaped community, which Kikutake had published in early 1959. After attending the conference, Tange commenced a visiting professorship at MIT in Cambridge near Boston, which was one of the major centers when we talk about cybernetics research. And he did this during the autumn term of 1959. There, he taught a course in architectural design titled New Community on the Sea, 25,000 Inhabitants on the Boston Bay. Tange afterwards presented the design based on that course at the 1960 World Design Conference in Tokyo, the event where the Japanese metabolist movement was founded by his mentees. But coming back to the cybernetic analogy of the biological growth of a tree, the proposal for Boston Bay took up Kikutake's tree and leaves analogy, but also went beyond it, asking, I quote, "Can the major structure not have the same possibility for growth as a tree trunk?" End of quotation. The plan for Tokyo was the answer to this question of large-scale cybernetic modularization. In addition to adding and removing houses representing leaves, the whole structure representing the tree's trunk had to be able to grow. The plan for Tokyo served to replicate the growth of a fully operational biological system, not just its short-lived organs like leaves. Growth of the whole civic axis, which you can see here marked red, would take place in 4 or more stages while remaining fully operational during expansion work. This civic axis was defined by transportation and communication networks, such as a highway and landlines for communication systems like telephones and so on. Its growth would be implemented at points in time when economic or demographic factors encouraged it. Tange Lab just switched the example of a growing tree trunk with the growth of a vertebral column in an embryo. I quote, "The system, meaning the civic axis, is composed of cycles, somewhat like the vertebrae in the spine. At each stage of development, the transportation system is complete, but there is no endpoint. At any point, it is possible to develop and extend it through another unit." End of quotation. Tange Lab's example of the vertebrae also further stressed a particular linear structure to be replicated by linearity, growing along communication and transportation networks. After all, the vertebral column provides the structure for the spinal cord, meaning a vertebrate's central linear communication highway, so to speak. For Tange, this flexible expansion of the linear communication and transportation networks would guide high population density urban growth, and therefore prevent uncontrolled horizontal urban sprawl. Such high population densities serve to reduce the environmental degradation that is otherwise attendant to urban sprawl, particularly if it happens on the ground level. I also want to emphasize that Tange was interested in Tokyo Bay, but as you saw on the images, his modular design was not limited to marine surfaces, which is a major difference to Fuller's ideas, which I want to come to now. Fuller arguably was the most controversial US designer of the 20th century. Dismissed twice from Harvard University as an undergraduate student during the 19-teens, he served as a naval officer during World War I, followed by several years of work in the construction business. After World War II, Fuller gained international fame through his promotion of the geodesic domes that are still strongly associated with him and which turned into a financial success. Fuller also became a major advocate of cybernetics in his urban design plans. In 1966, Fuller developed his tetrahedral city design for Tokyo Bay. In late spring of that year, during the heyday of the Japanese economic miracle, he had been contacted by businessman Matsutaro Shoriki and his staff to probe the technical feasibility and the economic costs of a building, the Nippon TV Tower, higher than Mount Fuji, which is 3,776 meters. Fuller and his team started working on the design for the tower in summer 1966, and soon afterwards received a modified request. What Shoriki now wanted to investigate was a possible solution for Tokyo's rapidly rising population by turning the Nippon TV Tower into a settlement for 1 million people, in addition to its function as television broadcasting tower. In August 1966, in response to the request to determine the cost of such a gigantic vertical settlement, Fuller began to think about an unsolicited alternative design, a floating tetrahedral settlement to be located in Tokyo Bay. Without question, this unsolicited design was a direct outcome of his meeting with Tange during a conference in July, where Tange discussed ideas of regional planning related to the plan for Tokyo 1960 and ideas of his mentees and students. Fuller then took up some of Tange's and also Kikutake's cybernetic ideas on how to implement growth, mobility, ecological autonomy, and adaptation to marine surfaces. Between August 1966 and May 1967, he unsuccessfully pushed Shōriki to consider his Tokyo Bay idea. Arguably an outcome of Shōriki's terrestrial mindset, one of his staff members emphasized that the 1 million people settlement should be part of the tower design, which, not really surprising, became too expensive for Shōriki. So what was original when we talk about Fuller's unsolicited idea? Where Tange used large physical infrastructures, such as highways and landlines, to create transportation and communication networks, Fuller aimed to disconnect from them as much as possible. His geodesic domes could be air-delivered, while his floating city design would, after construction in a shipyard, use the mobility that marine regions also gave ships and oil platforms. In this regard, floating oil platforms, which were built since the early 1960s, so when we talk about semi-submersibles, had another inspirational value. With increasing distance from the coastline, they were mainly connected not through large physical infrastructures, but through radio waves, helicopters, and ships. Fuller's aim for the tetrahedral city service systems was to make them largely ecologically autonomous. He strongly focused on using technology that allowed industrial growth while reducing pressure on ecosystems, here in the sense of a limited need to extract fresh water and to exploit and burn air pollution causing fossil fuels for electricity generation. To provide electricity for the structure, Fuller foresaw the integration of a small nuclear reactor. He therefore was able to propose a second benefit of the nuclear reactor by copying aircraft carrier technology. It could be used for desalinating bay water, providing the tetrahedral city with an ecologically autonomous freshwater service system. However, based on other historical examples, such as political quarrels over a Japanese nuclear-powered ship, it is very unrealistic that Fuller would have gained permission to host a nuclear-powered structure in Tokyo Bay. In terms of autonomy and mobility, one can understand Fuller's design as one of the amphibious transformations alternatives to large hydroelectric dams. Such dams were tools for storing and providing fresh water, regulating its availability all year around, and generating electricity. In the same sense, Fuller's structure supported energy generation and freshwater production. However, the average hydroelectric dam had a substantial ecological footprint through terrestrializing a huge space. Such dams also reduced sediment flux from upstream that often could not then compensate for erosion, meaning that many affected river deltas are sinking more rapidly than sea levels are rising. A large dam's removal would be extremely complicated and costly, while Fuller's design had a mobile ecological footprint. Mobility also strongly increased sustainability in the sense that these structures' full lifespan could be utilized, being relocated instead of demolished if it was not needed anymore in a certain place, similar to a floating offshore oil platform, and unlike terrestrial buildings. Fuller also explicitly mentioned earthquake resilience of floating structures as one of the reasons why he wanted to build such a huge settlement offshore in Japanese waters. There is no evidence that Tange or Fuller considered their marine urbanization designs to be utopian or technically unfeasible. This distinction is important. Without question, Tange Labs and Fuller's first proposals were, due to their size and shift to aquatic surfaces, highly provocative and served to attract public attention. So the size, to a certain degree, was not something that was to be taken fully seriously. They therefore received, as part of the global cybernetics boom, numerous contemporary responses, some very critical in both Japanese and multiple European languages. Moreover, feasibility did not automatically mean efficiency, considering that their designs were among the first of their kind. Aesthetically, in my view, they were debatable. Altogether, the actual implementation of their designs would have necessitated further, far more detailed plans, as well as a budget and construction regulation related substantial size reduction. For example, the plan strongly inspired the creation of Amsterdam's expansion district, Aalborg, since the late 1990s, albeit in a scaled down form. Fuller's modified and strongly scaled down version, Triton City, which in 1967, so 1 year later, proposed for US urban waterfronts, passed US Navy stability calculations in 1968 and contributed to studies at the University of Hawaii and the construction of Kikutakis Aquapolis, the floating city hosting the Japanese exhibition at the 1975 International Ocean Exposition in Okinawa. However, the terrestrial mindset among Japanese civil servants and many others focused on the control and removal of waters instead. In combination with a quite limited contemporary concern for reducing the ecological footprint of urbanization, the terrestrial mindset shaped their decisions regarding urban planning and regional development. There were also a number of other factors that made Fuller's and Tange's proposals unattractive, which I cannot go into the details here, but you can ask me if you're interested. So what are some of the long-term impacts of Tange's and Fuller's ideas on marine urbanization as one dimension of Earth's amphibious transformation? In particular, Fuller's Tokyo Bay design applied mobility also to individual dwellings and dwelling units. One could again think of leaves of a tree here. Among them, high-tech trailers or houseboats, which were to be based on the many layers of the tetrahedronal structure. This idea enabled Fuller to propose even stronger cybernetics-shaped modularization. After all, such modular dwelling units would be able to move between floating structures. In his design for US urban waterfronts, which you can see on this slide, his mobility and modularization ideas changed slightly and focused on bigger modular Triton City units for 5,000 people each, which could grow together into larger offshore settlements. Over the following decades, the cybernetics-shaped modularization of floating units was further contemplated. Current design proposals, such as the Bjarke-Ingels groups that was related to the aforementioned UN Sustainable Floating Cities Roundtable, utilized only mobile floating modular units. Together, they would form a growable structure. In terms of Tange's and Fuller's other cybernetic ideas, UN Deputy Secretary General Amina Mohamed's roundtable speech can serve as an example of the planned ecological autonomy of such structures. In her speech, she suggested that the adaptive floating structure could rely on generating its own solar power to mitigate climate change and fuel an electric vehicle-based transportation infrastructure. So it would not necessarily have to be connected to some kind of public grid. So Tange's and Fuller's cybernetic ideas of growth, mobility, ecological autonomy, and adaptation are still very present, even though the tree and vertebrate analogies are gone. These ideas mark a strong difference to terrestrial designs shaped by a terrestrial mindset. Moreover, in terms of Tange's and Fuller's cybernetic ideas, present smart offshore structures that are connected to the internet or may be connected to Starlink high-speed satellite internet during the next years are developing even more complex artificial communication systems. These complex artificial communication systems serve to replicate the evolutionary adaptation of biological communication systems to marine surfaces. Integrating new smart offshore structures into the Internet of Things results in more ecological autonomy as well as AI or artificial intelligence autonomy, which was one of cybernetics' main aims, but only very much in its early stages during the 1960s. Offshore structures are then not isolated, but enabled, like terrestrial buildings, to collect real-time data on damage and to make calls for repairs. or to receive meteorological information that through automation temporarily shuts down offshore wind turbines during an approaching strong storm, or rotates floating solar panels according to sunshine conditions, and so on. Offshore satellite network connections also mean that isolated offshore oil and gas platforms whose data is locally stored can move their data to a large cloud via the internet for analysis and storage. In the long run, such offshore satellite network connections will also extend ride-hailing services, something like Grab or Uber, maybe using self-driving water vehicles, to marine surfaces, based on current experiments in urban waters in the United States. Satellites also extend communication networks in other ways, beyond future high-speed internet access. Since the 1960s, satellite images have been providing weather data and capturing marine conditions, ranging from fog, icebergs, or the extent of oil spills, to surface temperature, and based on the water color, the amount of plankton in the sea. Machine learning and computer vision, as more recent forms of artificial intelligence, are now being applied to analyze satellite images to spot illegal fisheries, piracy, and trafficking activities, to support increasingly self-driving ships, and to recognize approaching natural disasters. Combining the historical and real-time data provided by satellite images with real-time Internet of Things data likely will be relevant for both the design of offshore structures as well as the ability to receive insurance for them, which is usually a condition for their mass construction. So to conclude regarding Earth's amphibious transformation and the still quite dominant terrestrial mindset, given the marine urbanization and industrialization driven amphibious transformation, the climate change adaptation and mitigation approaches of coastal cities should not be evaluated exclusively within a terrestrial mindset. Vulnerability to floods and storm surges, subsidence, erosion, and other disasters continues and in many cases intensifies. The human-caused rise of sea levels, which will continue for millennia due to the slow warming of lower ocean layers, will only intensify their impact. They are problems that cannot be fully dealt with within such a terrestrial mindset and its exclusive focus on controlling and removing water. After all, in this terrestrial mindset, amphibious or floating adaptation approaches are easily ignored, outright denied, marginalized, or branded utopian, even though Earth's surface has continued to experience an amphibious transformation through communication system expansion, as well as advances in fixed and floating offshore architecture and engineering. Thank you. End of my presentation.
All right, thank you, Stephen, for the very insightful presentation. So we'll open the floor to the audience. Is there any questions? You may post a question in the chat group, or you can just speak to the mic. Yeah. So what do you see as the challenges for these floating cities in general, and specifically for Singapore, for us to adapt, to build a floating, waterfront?
I mean, it very much depends what we define as a floating city. That's one of the problems that I came across all the time over the course of decades since the 1960s. I mean, there are some people who imagine this to be something like 50,000 people with a cathedral floating on the ocean somewhere, which is maybe a bit unrealistic. But if we scale up, so to speak, from what mainly the offshore industry has created, then you can actually call some of the offshore oil complexes or certain other buildings floating settlements, floating villages, and so on. I mean, it's also related to the question, how many people do you need to have a city? And another issue is also if you actually need to have people living there permanently. So one of the issues I briefly want to talk about is the issue of the functional separation of city districts. So one of the criticisms that Tange received, and which was very serious, is that he basically proposed a structure that would be split into residential quarters, commercial quarters, industrial quarters, and a gigantic highway that connected all of them. So you would not be able to walk, for example, to your working place. You would also not get without a car to a supermarket and so on. So this is totally different than the natural growth of a city, so to speak. So this is something that Fuller, to a certain degree, with a more focused modularization, wanted to deal with. But in the long run, even if you have only, so to speak, 5,000 people living on some floating settlement, and you then from the beginning tell them how many supermarkets they are supposed to have, this is also very much top-down centralized design approach. So one of the conditions, I think, to come to your question and how this can all develop in the future is not only very strong modularization, but also giving people the maximum freedom to actually put onto platforms what they really want. And if they want to have 3 supermarkets, just to give you this example, instead of 1, because they don't like the idea of a monopoly, there needs to be space, and there also needs to be a possibility to change existing structures in a way that this can be implemented in an easy way. So this is always the problem here. Another issue that I briefly want to talk about is basically starting in a certain way with first principles, and to ask really, if you want to build a floating city, what is really the main difference if you build a settlement offshore to a settlement onshore? What can you really do there that cannot be done onshore? And I mean, some of the points that I briefly touched are the mobility issue. This is more sustainable in the sense that if implemented in the correct way, buildings can be moved around and therefore do not need to be demolished. There's also less of an permanent impact, even though there are issues like shadow casting and so on. But altogether, in that sense, it's more sustainable than land reclamation. So you don't change this space landscape for the future generations. And I think one of the main issues for many politicians, at least in certain countries, is that it's easier to generate solar power. So that's I think one of the proposals that can go together with ideas for floating settlements, be that floating solar panels in not too rough waters, or be that roof installed solar panels for a variety of environmental reasons. I don't mean in the sense of environmental protection, but in the sense of the conditions offshore that make it easier to produce solar energy, and also to a certain degree to use the availability of offshore wind turbines. So
so in terms of the Tanguy's definitions of floating or amphibious dwelling, do they meant floating structures or anything that use this ocean space for development?
So in Tanguy's case, it was more amphibious or elevated. So this elevation basically meant that, I mean, the water level would go up and down, but would not reach the settlements on top of the piers. I mean, we are talking here about an idea that at the extreme points was supposed to elevate buildings more than 50 meters above the bay level. I mean, this was all, as mentioned, to a certain degree also for the media and so on. But I mean, some of the long-term impacts are, for example, I mean, if you walk around in Japan, you can see, and if you actually read some history books, that soon afterwards actually elevated highways were introduced. I mean, not to the degree that Tanguy wanted, and also not really over Tokyo Bay. I mean, there are some connections and so on, but there are quite a number of elevated highways in Tokyo to solve this urban congestion and transportation problem. And for Fuller, it had to be floating.
Mm-hmm.
It started basically, I mean, with this idea from Matsutaro Shoriki to have this really big building looked into, and Fuller was concerned about the stability. I mean, the question if this really can be built, they did some investigations and so on. It would be extremely expensive, as you can imagine, and you had to deal with high altitude winds and so on. So he came to the conclusion, in terms of earthquakes, that's not a good idea. If you have a big earthquake in Japan, better build something on the bay. And he also argued that if you want to build other tetrahedral like floating structures, then dig an artificial lake and place them in this artificial lake and not somewhere onshore. So, and for Kikutake, he was also very much focused on floating structures.
Okay, all right, thank you very much. So we have one question. Where do you think within the APEC region would be most ready to develop a floating city?
Here again, I mean, it largely depends on the question of regulations and so on, which government actually could be interested in doing that. And I mean, the environmental factors and conditions should also be taken into consideration. I mean, since yeah, the study done by Fuller, who already was concerned with hurricanes or more typhoons. I mean, if you have such an area that is affected by very strong winds, that's maybe not the best place to try some prototypes. I mean, maybe in the long run, but not for the first one, if you don't want to have it crash in some way. And otherwise, I mean, I could also go into details here why Fuller failed, and then mention, for example, if you remember this seasteading project in Tahiti, this was almost exactly what was criticized regarding Fuller's idea. Don't try to build your own kind of exclusive political zone, and also don't try to move anything into waters that are not controlled by a state, and don't try to get around state regulations. Also, if you remember this other seasteading story of Phuket, the American Thai couple, that's also the same story. And if you remember, maybe Gaylord Nelson, who's the founder of or co-founder of Earth Day, he actually wrote an article that was printed in the Congressional Record of the United States Congress, that Fuller basically had this idea to build floating cities that could be moved into international waters and then do there what they want. And that's something you cannot allow at all. So really make sure that the state is with you. Otherwise, this ends in a disaster, I think.
Right. So maybe a follow-up from these questions from Secretary Rina and Mars. So how do you see the future of floating cities as a government business or private investing?
So my take on that is that, I mean, that there are a number of different ideas how this could be implemented that I read in books. My personal take is that we probably see an increase in industrial structures ranging from solar energy, offshore wind turbines, which are already in the process of being built. Certainly also more and bigger mariculture facilities and so on. And then maybe similar to the offshore industry, the slow development of accommodation places, which at the same time maybe will not as important anymore, because probably also with large scale internet coverage, there will probably be more automation, be that underwater drones or flying drones and so on, that will be implemented there. So that's a kind of industrialization based floating city where you have basically an industrial focus and you don't focus really much on residential quarters. And then at the same time, in the long run, I also think that coastal cities will increasingly build or support the construction of floating homes and so on. So in that sense, you probably don't have the floating city that is in some ways independent or not really related to an onshore economy very soon. So because it's basically not really essential in view of a stronger focus of coastal cities on floating structures and a more industrial focus on something that doesn't need too many people living there.
Okay.
But I might be wrong in this regard.
Okay, so we have one question from Nachu. What's the key reason floating cities idea did not really take up? Because I read from one of your paper with the same title, this Shoriki says that it's cost in the 1970s, but how about now? Are we ready for floating city? Is the cost already ready to be economical?
I think today it would be possible. So it obviously depends on how you actually also support it with certain industrial facilities to actually generate some income and justify the overall costs for implementation. But yeah, just to give a few reasons why this didn't really take up. I mean, I mentioned briefly the issue that these ideas from Tange and Fuller were not really practical because they had this strong separation of different functions. So it was not comfortable to live there, basically, for people. Similar to the problems that many artificially designed onshore cities have. And there's a large literature and lots of complaints, starting with Jane Jacobs and so on in the 1960s, how you actually need to build a city that you have, for example, nice nightlife where you don't depend on a car and so on, and also have more security in the sense that you don't have any quarters that are almost empty after it gets dark, like, for example, industrial quarter where nobody lives and so on. I mean, this separation of spaces and functions goes back largely to the 19th century when you didn't want to have residential quarters next to pollution producing industrial quarters, but it's not really relevant anymore when people are basically engaged largely in tertiary sectors and commercial activities where you can mix this up. I also mentioned this concern that people would move floating structures into spaces that are not controlled by the government and engage in all sorts of practices there, which started, I think, in the United States with gambling, for example, outside the territorial waters and so on. But there was also then this concern for environmental pollution. There's also a variety of concerns that basically this is too much techno-optimism. That's now a cultural issue. And for example, Lewis Mumford, important urban studies person, wrote this article on pyramids as the first mega machines, basically with which pharaohs controlled the population by making them engage in a stupid construction project that basically kept them occupied. And in some ways, he also compared this, for example, to the Apollo program, basically, which was nice for a couple of people who then walked around on the moon, but almost everybody else just had to pay for it. And to a certain degree, also applied this to Fuller's idea, since, I mean, the shape of Fuller's structure, this almost pyramid-like shape, was also not helpful if your criticism basically starts with ancient Egyptian pyramids that are seen basically as this kind of technology-driven control function. There was also a reduced interest in ecologically autonomous structures, which is now getting important. I mean, it's not only about, I think, rising sea level. That's obviously a concern. But if you have intensifying floods and people really live in a disaster area and are hit by a disaster, which is maybe not necessarily happening in countries like Singapore or the United States and so on, but can happen in island countries, Jamaica, for example, then if you actually have a more ecologically autonomous structure with floating solar panels or with rooftop installed solar panels, you can actually produce energy while you are on your floating house for hours or days until somebody saves you or until the water retreats and you don't have to leave your house, because most likely somebody comes and steals all your things while you're away. So in that sense, you can also, if you have solar energy, produce your own water, or you can collect water on the rooftop and so on. So that's also something that I think is getting more important when we think through the implications of climate change, rising sea levels, flood disasters, and so on. And one last point, Fuller was also just not going on with this project anymore because he became occupied with other things. So you can also say that he just had other ideas in this regard. So yeah.
So in the past, Japan opted for land reclamation, right? So now with the rise of seawater level, you see that this floating city concept will be more acceptable to this kind of concept? And do you think that this floating city is effective in the protections of rising sea water level?
I mean, in terms of protecting against rising sea level, I think almost everything that floats is helpful, and it's also more comfortable for people than elevated buildings. When we talk about older people, they either need an elevator or they need stairs if you really elevate a structure. And I mean, the elevator, if you have a flood, isn't really helpful. The stairs are not really nice for older people to walk every day. So floating in that sense is certainly the better approach. Here again, the question is, I think, the size. That's certainly something I can imagine more that many people will build individual floating homes or maybe small clusters of them. If this moves into a bigger structure, I can also imagine that, but it certainly takes longer because, I mean, for people, I mean, there are also issues like privacy and also, I think, for a long time, better connections to onshore infrastructures and so on. So there's this maybe takeoff point in time where you actually can have a city that can sustain itself, but it would probably still be based somewhere between an onshore city and some floating industrial combine. So, and I mean, if this gets really implemented by the government, I think it's to a certain degree, it's a question of explaining to government officials what the benefits are. And this can take a very long time. I don't want to go into details, but I mean, in Germany and other countries, we recently had these floodings. And I mean, these floodings, they happen since, I mean, you can find this online easily, all the sources since the late Middle Ages. Everybody knows this is an area that gets flooded every couple of years. The question is just how strong are these floods? But I mean, politicians came to the conclusion we can remove all the public sirens. We don't need to send any text messages to people and so on. So sometimes you really wonder what is going on there.
Okay, all right. Okay, we have one question from Prof. Alan. What is the more likely driver of floating cities, humanitarian crisis or voluntary migration?
My take, I'm talking here as a historian, is I think humanitarian crisis, or at least preparations to accommodate sea level rise and or to adapt to sea level rise and the related crisis. Whereas voluntary migration, in theory, sounds good, but the question is also a lot of states historically want to control where you're actually going to, or want to control what you may be doing on such a place. I mean, I already mentioned the issue concerning Fuller and not moving any structure into waters not controlled by a state and so on. But I mean, Fuller explicitly said that he actually wanted to liberate people from governmental oppression and governments not allowing people to move where they want to move to. But at the same point in time in the 1960s, think about the German Democratic Republic and the construction of the Berlin Wall, or think about North Korea and so on, and the minefields and so on. So you find quite a lot of countries, and these are the countries where people most likely would like to migrate, that will not allow people to migrate or will make it very, very difficult for them. Whereas people in a lot of other places, I mean, yeah, you have market libertarians and so on who would probably do some kind of seasteading project, but that's a very small number of people, and in terms of a lobby group, maybe also not the strongest. So I think this voluntary migration idea is good in theory, but will not have the real driving force at the end of the day.
Okay, so there is no more questions from the chat room. Any other questions? If no, probably we can stop here. Thank you very much, Dr. Steven, for giving this presentation. So I'd like to thank everyone once again for attending this webinar. And please do look out at our society webpage for future activities. Thank you, everyone.
Thank you. Thank you.
Yeah, thank you, Steven. Thank you.